Alright, we're going to have a really quick video to show us how to do the cross product when your vectors are written in unit vector form. Previously, in our work, we used this definition to calculate the force of a charged particle moving in a magnetic field. We relied on the fact that the cross product in magnitude is equal to QVB times the sine of the angle between velocity and magnetic field, and that we could use the right-hand rule to figure out the direction. So in this case, though, our vectors are given to us in unit vector form, and we need to know how to do the calculation in that situation. We could simply substitute into our expression of QV cross B. Our velocity is 5 meters per second. It's in the z direction. And our magnetic field is given as 3I minus 4J. We could simply use the distributed rule and multiply K cross 3I and the 5K cross minus 4J. To do that, we have this little reminder of how it works. If we draw the three unit vectors, I, J, and K, we can remember that if we're going around in the clockwise direction to find the cross product, the answer is the next vector. So I cross J gives me K, J cross K gives me I, K cross I gives me J. If we have to go backwards in order to do the cross product, it's the next vector, but it's negative. So I cross K is minus J, K cross J is minus I, etc. So we could use this to do this calculation because the vectors are pretty straightforward. But if our velocity had more than one component and also our magnetic field had 2 or 3 components, it would be very tedious and it would be hard to actually avoid making a mistake. So what I want to show you is how we make a matrix that we're going to use to calculate V cross B. So the way that we write it, the matrix V cross B, is the top row are the unit vectors, the next row is the velocity vector, and it's always x component, y component, z component. And then finally, the third row is the vector for the magnetic field. So that's 3 and minus 4 and 0. Basically, what this expression is telling us is that V cross B can be found by the determinant of this 3 by 3 matrix. I'm going to show you one way that we can find this determinant, because a 3 by 3 is not as easy to do as a 2 by 2. But the way that I'm going to show you is going to allow you to have all the components grouped together. What we're going to do is we're going to expand this matrix, the determinant of this matrix, about the top row, which means that we're going to take each of the elements in the top row, which is the I, J, and K, and multiply them by the matrix, the 2 by 2 matrix that remains if we eliminate the row and column that I is in. So it makes more sense once you see it. So the first term is I, and then I'm going to give a 2 by 2 matrix. The 2 by 2 matrix is the matrix that remains if I eliminate the row and column that I hat is in. That leaves these 4 terms right here. So I got 0, 5, minus 4, and 0. Then the j term, and we just have to remember that a negative sign goes in front of the j term. And we eliminate the row and column that j comes in. That gives us 0, 5, 3, and 0. And then lastly, we have the k term in the 2 by 2 matrix by eliminating the row and column that k is in. It gives me 0, 0, 3, and minus 4. And so now, each one of these terms is the x, y, and z component of our answer of v cross b. Remember, to find the determinant, we multiply by these two terms, and then we subtract going the other way. So in front of I, we get 0 times 0 minus 5 times 1. The second term for j would be 0 times 0 minus 5 times 3. And then the last component is 0 times minus 4 minus 3 times 0. Continuing, v cross b looks like this, just simplifying things a little. And so we found our v cross b is 20I plus 15j. So then this would be multiplied by the charge, which we actually found q was minus 1 times 20I plus 15j. And if you remember when we did in class, when we were trying to sort of use the right-hand rule without the mathematics, we said this was our magnetic field direction. This was our velocity. We said v cross b was sort of in that quadrant, but because of the negative charge, our force would be in the opposite direction. Notice that this stands true. Our force has a negative x and a negative y component, and so it all makes sense. And that's how you can do the cross product if in unit vectors.